she's also at WITS, and she's a new Deputy Director for the ARUA Center of Excellence in Materials, Energy and Nanotechnology. So please take it away. Thank you. Anything?
Can you hear me?
Now I can, thank you.
Okay, can you see my screen?
Yes, thanks.
Okay. Good morning, everybody. My name is Nosipho Moloto, and I'm going to try today and share with you the work that we do around hydrogen evolution electrocatalyst. So as alternatives for platinum. Before I begin, let me start by introducing our group. About 6 PIs. Can you hear me?
Yes. So
okay. Yes, we're made up of 6 PIs, myself and 5 others who in fact 4 of them are members of the Center of Excellence in Strong Materials. And we work in various areas around semiconductor nanocrystals, as well as carbon nanomaterials. And in this team, we then supervise a number of, postdocs, PhDs, MSCs, and so forth. And in fact, in terms of the collaboration, I should have added ARUA here. This is an old slide, but we work closely with the School of Physics, COE, Strong Materials, MEDGE, which is actually one of the groups that kind of merged. I come from MEDGE, so merging with the COE in Strong Materials to be part of the ARUA Center of Excellence in Men. So yeah, so without further ado, let me go straight into our presentation. So why hydrogen? So I wanted to talk about hydrogen. So I work in energy, looking at photovoltaics as well as hydrogen generation through electrochemical methods. So why do we want to do hydrogen? And in this case, I specifically say green hydrogen, because virtually any primary energy can be turned into hydrogen. And so this opens up, possibilities of hydrogen becoming a universal fuel. And also green hydrogen, as some people might know, will contribute to our national energy objectives. So we want to, there's quite a lot of push by the government to go towards hydrogen. And that's because it can increase our energy security. We want to diversify our energy sector so that we're not so reliant on coal. And of course, environmental stewardship, meaning that the green hydrogen is considered to be a cleaner fuel than normal fossil fuels. And then, of course, economic competitiveness. We want to have alternatives so that the business continues as usual. You don't want load shedding due to whatever issues with coal or and so forth. So to have alternative is not a bad idea. So it can increase our economic competitiveness. And then, of course, using hydrogen as an energy vector helps to mitigate the intermittency of renewable energy. So with PV, we know that, it relies on the sun. When there's no sun, it sort of has an issue. With hydrogen, because you can store it, so it then sort of, it's always available in a sense. So how do you make hydrogen? There are various ways. The renewable or nuclear power, so meaning that it's using clean source. And in our case, we're interested in this way, it is using clean source of energy. to actually drive an electrolytic process or electrolysis so that you can get what we call green hydrogen. So green hydrogen is known to produce little or to no carbon dioxide emissions. And then you have from natural gas and coal, you can also produce hydrogen through a process from natural gas called steam methane reforming. And then from coal, it's called gasification. If you then do carbon capture, then the hydrogen produced is known as blue hydrogen. And again, it is decarbonized. But if you do not do any carbon capture, then it becomes gray hydrogen and brown hydrogen, depending on the source of energy that you are using. And then straight from the grid, of course, you can power electrolysis straight from the grid. And that hydrogen is just known as hydrogen. So of course, then what determines whether it becomes brown, blue, gray, or green is what is the source of that electricity from the grid. So you can, in effect, when you increase the number of renewable energy into the grid, you can see that that this process, this hydrogen here, can start to turn and become more towards the green. So I mean, our interest is obviously on green hydrogen. So electrolysis, so what is it? Electrolysis water splitting. So electrochemical water splitting, and for hydrogen, we tend to shorten it to say hydrogen evolution reaction, because we actually looking at that half reaction that occurs in the cathode where hydrogen is produced. So water is split over the top reaction is the overall reaction where you have water and it's split into hydrogen and oxygen. But in the cathode, this is where your hydrogen is generated. And in the cathode, you have an electrocatalyst, and this is what we are interested in the electrocatalyst that actually drives this dissociation of hydrogen ions into hydrogen. And then, of course, on the anode, you have the balancing half equation, which is the formation of oxygen. And all of this, or the splitting of water occurs on the surface of a catalyst. And since I'm from chemistry, our interest is obviously on this catalyst and how we can design it to actually do this process more efficiently. So the mechanism for hydrogen evolution reaction is shown here in the slide. On the right is when you're using alkaline conditions. Commercially, the alkaline conditions are preferred because it's a bit more easier to work on with alkaline conditions rather than acidic conditions. But of course, if you have to think about it, if you're trying to make hydrogen, an excess of hydrogen is actually more desirable. So many of us, including us, we study the hydrogen evolution reaction both in acidic media and in alkaline media. So the presentation for today, I'm going to focus on the acidic media. What is important here is that, of course, you have electrons coming from your source of energy, and then you have an excess of hydrogen ions, and these hydrogen ions are adsorbed on the surface of the catalyst. And then there are two pathways which this can go. You can either get an additional hydrogen from the water because it's acidic, there's extra hydrogen ions, through a process called Herovsky's step, where the two hydrogen atoms, one that is adsorbed and one coming from the solution, react to form the hydrogen gas that we need. Or you can actually have another hydrogen ion from the solution adsorbing onto the catalyst surface. And then with the energy source, or from electricity or from renewable energy, this drives these two hydronium ions, or these radicals to react, and then you form hydrogen. And this step is called the Tafel step. So usually depending on what you get, you can see the values here. The Volmer step occurs almost always because that signifies absorption of your hydrogen ion into the electrocatalyst. And then it can either go towards the Herofsky step or the Tafel step. But usually what we see is something in between where both these reactions are, or both these pathways are happening at the same time. And the indicator for that is what we call the Tafel slope. So the value of a Tafel slope will kind of give you an indication of what mechanism does your HER follow. So what's wrong with the HER? Well, I mean, the use of the platinum electrocatalyst, while it's very good, but it drives the cost. As such, making, you know, hydrogen energy not desirable because it's costlier than your normal fuels that you get in a fuel pump. So that's the problem. So we need to find strategies to actually find alternatives to platinum or lessen the amount of platinum used so that we can drive the costs down. Another problem is sluggish reaction kinetics due to the high overpotential. So to overcome this, we are at the moment looking at two strategies. We want to use alternative materials as electrocatalysts that are not 100% noble metals so that we can drive down the cost, as well as find strategies to improve the reaction kinetics and the efficiency of these alternative materials. Because, I mean, platinum is used for a reason. It's actually pretty good in hydrogen evolution reaction. And then, so once we do that, we then want to evaluate the performance of the hydrogen evolution reaction catalyst. And we can do that by looking at its activity, stability, and efficiency. And the activity, we can determine that from the onset potential, the overpotential, the Tafel slope, and the exchange current density. I'll explain this in the next slide, what is that, what is actually these parameters. And then, of course, the stability by the change of the overpotential or the current over time. You can study that and see how that is changing over time, and that will tell you how stable your catalyst is. Of course, a good catalyst is a catalyst that is stable for a long time. And then we can look at the efficiency by studying the Faradic efficiency and the turnover frequencies in terms of the experimental results versus the theoretical predictions. Just to briefly explain some of these parameters so that when I go to the results, I mean, everybody is on the same page. So the onset potential, or let me start with the overpotential. The overpotential is the difference between the applied potential and the thermodynamically determined potential for the hydrogen evolution reaction. And this is about 1.23 volts at standard temperature and pressure. And then also the onset potential, this is actually in the graph below, it's that green region on your left-hand graph. It's the potential or the overpotential at which the catalytic current is first observed. So when that graph bends and you start generating current, you know that the reaction is occurring or the catalysis is starting to happen. So that is called as the onset potential. And then you have your Tafel slope and the exchange current, which can be determined from this equation and the bullet point 3. And the Tafel slope is related to the catalytic reaction mechanism in terms of electron transfer kinetics. So how you use the Tafel slope to determine whether the mechanism is Herofsky or is Tafel's pathway or a combination of any of the three. And then the exchange current density describes the intrinsic charge transfer under equilibrium conditions. A higher current exchange current density means a greater charge transfer rate and a lower reaction barrier. So you know in catalysis that we are always looking for a lower reaction barrier, meaning that the reaction can easily occur and you can get your product. In this case, our product is hydrogen. So for a catalyst, okay, you have 5 more minutes. So you have lower B and a higher A for a good catalyst. So I have to move fast. and then Faraday efficiency and turnover frequency. Using these equations, you can determine it. So I'm gonna probably, because I don't have time, I'm gonna look at like one case. Instead of the 4 cases that I've put here. So we wanna use 2D layered nanomaterial as an electrocatalyst, and then we wanna study the effect of the structural motion, activity, and stability. So let's look at the first case or maybe let's look at the surface functionalization of rhenium selenide. So I'm gonna skip this one. Selenide, you tend to improve, as you can see, with these values, you tend to improve your the production of hydrogen evolution. But let's look at surface modification. So you can actually modify the surface of your rhenium selenide, because when you make these particles, you have to have a stabilizing agent. But what we saw is that it's important to choose the right stabilizing agent. Like we tried 3, which is oleolamine, oleic acid, and triphenyl phosphinoxide. What we saw is that on the surface of the nanocrystals, how these 3 molecules interact with the surface is different. You see that on the simulation on the right. And maybe another important thing is that topo, which is a C in this case, triphenyl oxide, is a bulkier molecule. So you tend to have less of it on the surface compared, let's say, to oleolamine, which is smaller. Therefore, it covers the surface quite substantially. And another important thing is that topo interacts with the surface. We can see that in the simulation less strongly, or it doesn't bind strongly to the surface as compared to oleolamine. And that has significance in your hydrogen evolution reaction. And you can see that it also affects morphology. They're slightly different while they look similar because they're all rhenium selenide, but there is some subtle differences. So what we see is that obviously on the right, I just don't have a pointer, I don't see. Your platinum is actually the lowest onset potential, you can see. And then rhenium selenide oleolamine has the highest. So what it means is that rhenium...
2 more minutes, 2 more minutes.
Rhenium selenide is actually a poor electrocatalyst as compared to platinum. And in terms of the topo, you can see that it's actually quite near. It's a red curve. It's quite closer to the platinum. The platinum, obviously, it's the state of the art. It's got a slow slope of about 31 millivolts per deck. And then the topo follows with 58. So again, telling you that topo is actually better than oleic acid and oleolamine. All the other results follow the same trend. And basically the conclusions we can make from that is that topo is the best electrocatalytic activity. Ola has the largest number of molecules on the surface, therefore it blocks the active sites. Whereas topo, being bulkier, allows for less molecules on the surface, it's freeing the active sites. And also topo therefore allowing dynamic adsorption and desorption, therefore not blocking the active sites. Okay, so I'll move on here. I thought I had more time than needed. So basically, I can't go through all the other ones. But what maybe the take-home message is that you can actually modify structures of these nanomaterials, 2D nanomaterials, and you can see that by manipulating the structure, you get different activities and you can improve. So you can engineer the structure of these materials through doping, through surface modification, as well as through activating the material. You see improvement. Thank you.
Thank you very much for a lovely presentation. Sorry, I had to speed you up.
All right, no problem.
Thanks. That was really nice. And it's really good to see the team there.